In this example, we're looking at a 2-degree of freedom system that's made up of blocks 1 and 2 and 3 springs and 3 dashpots. The masses are all the same for the 2 blocks. The springs have the same stiffness of K, and the dashpots have the same damping coefficient of C. We're asked to come up with the equations of motion for 3 different combinations of coordinates. In A, absolute coordinates x1 and x2 positive to the right. For figure B, absolute coordinate y1 to the right, absolute coordinate y2 positive to the left. And then figure 3, absolute coordinate z1 to the right, and z2 being the motion of 2 relative to 1. We want to come up with, again, the equations of motion for those coordinates. So we're going to end up with 3 different sets of equations of motion. So let's draw the free body diagrams for A. For coordinate x1, that spring force is going to be kx1, and when x1 is plus, a block is to the right, the spring is stretched. Same kind of thing here, cx1 dot. For the spring between 1 and 2, that spring force is going to be the difference between x1 and x2. So let me write this x2 minus x1. And when x2 is larger than x1, the spring is stretched. It's going to pull on the block 1. It's going to be pulling to the left there in block 2. Same way here for the dashpot force there of C times x2 dot minus x1 dot. The spring on the right side, that's going to be K x2. When x2 is plus, the spring is compressed, points to the left. Same way here for Cx2 dot is that. We have the applied force of F. For B, same kind of thing, because y1 and x1 are the same. This is Ky1, this is Cy1 dot. Where it's different is the force in between. Here, y1 and y2 are positive pointing different ways. So when y1 and y2 are both plus, the spring is compressed, and that compression is going to be the sum of those two. That's ky1 plus y2. Compress when y1 and y2 are both plus, equal and opposite force on block 2. Same way for the dashpot force of C, y1 dot plus y2 dot is that. The spring on the right side. When y2 is plus, the spring is going to be stretched, it's going to be pulling, it's going to be pointing to the right. So this is going to be ky2 dashpot force cy2 dot. The applied force F. So we see the FBDs look quite different. For the third case, Z1 and X1, Y1 are all the same thing. So this is going to be K Z1 C Z1 dot. In this case, Z2 is relative to 1. The force on the spring is proportional to the relative displacements of the ends. So it's just K times Z2. When Z2 is plus, the spring is stretched. So it's going to be pulling to the right on that block. The equal and opposite force by Newton's third law is pointing to the left. Same kind of thing here for the dashpot force there of C Z2 dot. The spring on the right side. That's compression is going to be Z1 plus Z2. Recall that Z2 is the relative motion of 2 with respect to 1. So that compression there on the right side is going to be the sum of those two. When Z1 and Z2 are plus, the arrow points to the left. Same way down here in the bottom, C Z1 dot plus C Z2 dot. Again, when we look at the 3 different situations, the FBDs look quite different. Let's see how they affect the equations of motion. If I look at block 1 for case A. So when the sum force is in direction at x1, I get minus k x1 minus c x1 dot the forces on the right-hand side is going to be plus k x2 minus x1, c x2 dot minus x1 dot is that ma. A in this case is just x1 double dot. When I sum forces in the x2 direction, that's positive to the right, I get minus k x2 minus x1 minus c x2 dot minus x1 dot minus k x2 minus c x2 dot plus the applied force F, and that's equal to m x2 double dot. So these are the equations of motion for the set of coordinates what we call x. For B, there's some forces in y1. That's y1 against positive to the right, so that's a minus k y1 minus c y1 dot minus k times y1 plus y2 minus c y1 dot plus y2 dot, and that's equal to my1 double dot. F equals ma, and the acceleration, the absolute acceleration here is y1 double dot. The second equation, there's some forces in y2. Keep in mind that y2 is positive to the left. So that's going to be a minus k y1 plus y2. There'll be a minus c y1 dot plus y2 dot, like this. Again, y2 is positive to the left. And then this is going to be minus k y2 minus c y2 dot minus applied force F, and that's equal to my2 double dot. So these are our equations of motion in terms of y. Let's look at case C. Summing forces in the direction of Z1. That's going to be minus k Z1 minus c Z1 dot. I'm going to have a positive kz2 plus cz2 dot, and that's equal to, I think there's only four forces there, that's in ma. The absolute acceleration in this case is z1 double dot. Now for block 2, when I sum forces in the z direction, what I end up with here is minus k z2 minus c z2 dot. I get a minus k z1 plus z2 minus c z1 dot plus z2 dot, and that's equal to mass times the absolute acceleration of block 2, which is not z2 double dot, but it's actually z1 double dot plus z2 double dot. So that's the difference among those three different possibilities. It's to your advantage to write down what the mass matrix, the damping matrix, and stiffness matrix is for each case. And you will find that for A and B coordinates, those matrices will be symmetrical. It turns out, for the case C, the matrices are not symmetrical. So this is one thing we're going to observe about using the Newton approach, is that our matrices do not always end up being symmetrical, which for you may not be any big deal, but what we'll find out when we use an energy approach, that approach will always give us symmetric mass, damping, and stiffness matrices.